Earlier, we defined the electric potential, or voltage, at a point in space due to a point charge Q was defined as the potential energy per unit charge in the electric field of Q, and we got KQ over R, where R is the distance from any point in space to the charge. We can't use the same approach to calculate voltage within these infinite planes because of the great amount of charges present. V will not equal KQ over R for this region of space. For the parallel plane configuration, however, we can derive a very simple equation, a very powerful equation that relates voltage and the electric field. We're going to use the relationship of work to potential energy. The potential energy of a system with a conservative force is potential energy is negative of the work done by the force from the field. Since the electric force is conservative, we can use this equation. The potential energy is the negative of the work done by the electric field. Work is defined as F delta X, and then we make this interesting substitution here. What we're able to do here, which we couldn't do for the point charge, is come up with a constant value for force, because the electric field between the planes of this infinite plane system is constant. So we go ahead and replace F with QE, and the charge moves through a distance delta X. So let me erase that so you can see what we're doing next. We will now divide both sides by Q, and we're going all the way back to here to the potential energy. So we have potential energy divided by Q equals minus E delta X, and then we know that the potential energy divided by Q is a definition of voltage. So we're going to use the delta V symbol here. When we originally did it, we assumed that we started at infinity where the voltage was 0, so we could get an absolute value for V. Here we're not going to assume that. So delta V is minus E delta X, so let's box that one up, or E is equal to minus delta V over delta X. If our infinite planes are separated by this distance d, we can find the voltage difference between the two planes. Delta V is Vf minus V0, so delta V is minus E delta X. And what's delta X here if I take a charge and go from here to here or from here to here? Delta X is d. So I have delta V equals minus ED. The electric field points in the direction of the force on a hypothetical positive test charge. So let's kind of repeat what we did earlier. So if I have a bunch of positive charges up here creating a field, and I have the negative down here for the infinite parallel plane, the force is down. Okay? If we have a positive charge in the middle here, it feels a force due to the electric field in the down direction. And we already know that that means its potential energy is decreasing. So this electric field vector is pointing from a higher to a lower electric potential. The negative sign here tells us that. It means that objects in a field feel a force directed from locations with a greater potential energy up here to locations with lower potential energy. This applies to all forms of potential energy. We've been using gravitational energy as an analog, and it certainly works there. Another way to understand the negative sign here is to consider that just like a mass falls down in a gravitational field, like we discussed previous, from a higher gravitational potential energy to a lower, a positive charge falls down, and it's not really falling, it's just moving from a higher electric potential to a lower value. Just another way to look at it. We now have a new way of expressing the units for electric field. If you look up here, this is change in voltage over displacement, so that would be volts per meter. So we can also say electric field is volts per meter. Now let's see how we get the newtons per coulomb that we talked about earlier. A volt is energy per charge, so it's joules per coulomb. So we now have joules per coulomb over meter. We come down here, what's a joule equal to? A joule is a newton meter. So we now have newton meters per coulomb divided by meter. We can now cancel out the meter. We'll do it again here. And we come up with newtons per coulomb. So an electric field can be expressed either as volts per meter or newtons per coulomb.